Long before the first spacecraft ever lifted from Earth's surface, humanity gazed upward at the night sky with wonder. Among all the celestial bodies that dotted the darkness like scattered diamonds, one captured our imagination more than any other. There, in the velvet expanse above, hung a reddish point of light that ancient peoples named after their god of war, Mars, the red planet. For thousands of years, Mars remained a mystery, wrapped in the soft glow of distant firelight. Ancient astronomers tracked its wandering path across the heavens, noting how it seemed to move backward at times, dancing among the fixed stars in a celestial ballet that spoke of worlds beyond our own. They could not have known, those patient watchers of the night, that their distant red companion would one day become the destination of humanity's most ambitious journey. As centuries passed and telescopes grew more powerful, Mars began to reveal hints of its true nature. Through the eyepieces of early instruments, observers glimpsed what they believed to be continents and seas, polar ice caps that grew and shrank with the seasons, and mysterious dark markings that seemed to change with time. Some astronomers convinced themselves they saw straight lines crisscrossing the planet's surface, canals perhaps, constructed by an ancient civilization struggling to bring water from the poles to their dying world. These romantic notions, though ultimately proven false, served a beautiful purpose. They kept alive the dream that somewhere out there, across the vast darkness of space, we might not be alone. They inspired generations of storytellers and scientists alike to imagine what wonders might await us among the stars. And as the 20th century dawned, bringing with it technologies that previous generations could scarcely have imagined, that dream began its transformation from fantasy into possibility. The journey toward Mars truly began not with rockets and computers, but with dreamers and pioneers who refused to accept that humanity's place was confined to a single world. Scientists and engineers worked through long nights, solving problems that had never been encountered before, creating technologies that existed only in imagination. Each small success built upon the last, like careful stones placed one by one to construct a bridge across an impossible chasm. By the middle of the 20th century, the space age had dawned. Satellites began to orbit Earth, and before long, humans themselves ventured beyond our atmosphere. The moon, Earth's ancient companion, welcomed human footsteps in that remarkable summer of 1969. But even as those first lunar explorers walked in the gray dust of another world, their eyes, like those of all humanity, were drawn toward that next destination, that ruddy beacon that had captivated our species since the beginning of recorded history. Mars called to us across the darkness, and we prepared to answer. The road to Mars was not built in a day, nor even in a decade. It was constructed slowly, carefully, through the efforts of countless individuals who contributed their genius, their dedication, and sometimes their dreams to a collective endeavor larger than any single person or nation. Each mission that ventured toward the red planet, whether it succeeded or failed, added another crucial piece to the puzzle of interplanetary exploration. In the 1960s, as humanity was still learning the fundamental lessons of spaceflight, the first tentative probes began their journeys toward Mars. These early missions were fraught with difficulty. The distance alone was staggering, requiring spacecraft to travel for months through the emptiness of space, farther from Earth than any human-made object had ever ventured. Many of these early pioneers were lost, their signals fading into silence as they tumbled through the void or crashed upon the Martian surface. The Soviet Union, determined to be first in yet another arena of space exploration, launched a series of Mars probes beginning in 1960. These early attempts met with various misfortunes. Some failed to escape Earth's gravity. Others lost contact during their long voyage. But the engineers and scientists persevered, learning from each setback, refining their designs, improving their systems. Failure, they understood, was not the opposite of success, but rather a stepping stone toward it. In 1965, hope turned to jubilation when an American spacecraft named Mariner 4 became the first probe to successfully fly past Mars and return images. The photographs, grainy and imperfect by modern standards, revolutionized our understanding of the red planet. Instead of the Earth-like world that many had hoped to find, Mariner 4 revealed a desolate landscape marked by ancient craters, a world that appeared more moon-like than Earth-like. It was disappointing to some, but to scientists, each new piece of information was precious, bringing us closer to understanding our neighboring world. More missions followed. Mariner 6 and Mariner 7 flew past Mars in 1969, returning additional images and data. Then came Mariner 9, which achieved something remarkable in 1971. It became the first spacecraft to orbit another planet. For nearly a year, Mariner 9 circled Mars, mapping its surface in unprecedented detail. The spacecraft revealed that Mars was far more complex and interesting than those first Mariner 4 images had suggested. Enormous volcanoes rose from the surface, including Olympus Mons, the largest volcano in the solar system. A vast canyon system, later named Valles Marineris, stretched across the planet's face. And, perhaps most intriguingly, dry river channels carved into the landscape suggested that water had once flowed across the Martian surface. Meanwhile, the Soviet Union continued its own ambitious Mars program. In 1971, they launched 2 missions, Mars 2 and Mars 3, each consisting of an orbiter and a lander. The Mars 2 lander crashed during its descent, becoming the first human-made object to reach the Martian surface, albeit unsuccessfully. But Mars 3 achieved something historic. On December 2, 1971, it became the first spacecraft to achieve a soft landing on Mars. For a brief, tantalizing moment, Mars 3 functioned perfectly. It touched down gently on the surface and began transmitting data back to Earth. But then, after only 14.5 seconds, contact was lost. Whether it was overcome by a massive dust storm that was raging across the planet at the time, or whether some technical failure occurred, we will never know. Those few seconds of transmission, though frustratingly brief, represented humanity's first successful contact with the surface of another planet. The Mars 3 experience taught engineers crucial lessons about the challenges of landing on Mars. The thin atmosphere, the dust storms, the cold temperatures, the vast distance from Earth that made real-time control impossible. All of these factors had to be accounted for in designing future missions. The door had been opened, but only slightly. Much work remained to be done. Through the early 1970s, both Soviet and American missions continued to probe the mysteries of Mars. Some succeeded in their objectives, others failed, but each contributed to the growing body of knowledge about what it would take to safely land a sophisticated scientific laboratory on the Martian surface. and have it operate long enough to conduct meaningful research. By 1975, after years of planning, design, testing, and preparation, NASA was ready to attempt the most ambitious Mars mission ever conceived. It was called Viking, and it would forever change our relationship with the red planet. In the great halls of NASA's planning rooms, engineers and scientists gathered around tables covered with blueprints and calculations, their faces illuminated by the excitement of possibility. They were designing not one, but two complete Mars missions, each consisting of an orbiter and a lander. These would be the most complex robotic explorers ever sent to another world, carrying more scientific instruments than any previous planetary mission, designed to spend not days or weeks, but years studying Mars from both orbit and surface. The Viking project was, in many ways, a reflection of its time. The Apollo program, having successfully landed humans on the moon, had shown the world what was possible when a nation committed its resources and its will to a seemingly impossible goal. Now, as the Apollo program wound down, the expertise and infrastructure developed for lunar exploration would be directed toward a new target. Mars, the next frontier, would test whether the lessons learned from Apollo could be applied to robotic exploration of distant worlds. Each Viking spacecraft would be launched as a single unit, with the lander nestled within the orbiter for the long journey through space. This arrangement made sense both practically and symbolically. The orbiter would serve as both spacecraft and guardian, carrying its precious cargo across millions of miles of emptiness, then remaining in orbit to serve as a relay station, passing data from the lander back to Earth while conducting its own important observations of the planet from above. The landers themselves were marvels of engineering. Roughly triangular in shape, they stood on three legs like patient metal insects, equipped with every instrument and sensor that 1970s technology could provide. Two cameras would provide stereoscopic images of the landing site. A weather station would monitor Martian winds, temperatures, and atmospheric pressure. A seismometer would listen for Marsquakes. A sophisticated robotic arm would scoop up soil samples and deliver them to a suite of instruments designed to analyze their chemical composition. But perhaps most exciting, and certainly most ambitious, were the biology experiments. Three separate instruments would search for signs of life in the Martian soil, looking for evidence of metabolism, growth, or photosynthesis. The possibility that these instruments might detect living organisms on Mars, even microbial ones, added an element of profound significance to the mission. Viking might answer one of humanity's oldest questions: are we alone in the universe? The preparation for Viking involved thousands of people working in laboratories, clean rooms, and testing facilities across the United States. Every component had to be tested and retested. Every system had to have backups. Every procedure had to be practiced until it became second nature. The margin for error when sending delicate scientific instruments to another planet was essentially zero. There would be no second chances, no opportunity to send a repair crew if something went wrong. In August 1975, Viking 1 was ready. The spacecraft sat atop a Titan III rocket with a Centaur upper stage, a combination powerful enough to break free from Earth's gravity and send the payload on its interplanetary trajectory. On August 20th, 1975, the rocket engines ignited and Viking 1 began its journey. 3 weeks later, Viking 2 followed, embarking on its own nearly identical mission. For 11 months, the twin spacecraft sailed through the darkness between worlds. Ground controllers monitored their progress, making small course corrections when necessary, checking and rechecking systems, ensuring that everything remained in working order. The journey itself was a kind of quiet miracle, a testament to the precision of orbital mechanics and the reliability of space technology. As the months passed and the distance grew, Earth gradually shrank in Viking's cameras, while Mars slowly expanded from a distant point of light into a visible disk, then into a world with features and details. The waiting, for those who had invested years of their lives in the project, must have seemed endless. But they had learned patience. Space exploration operates on its own timeline, measured not in hours or days, but in the months and years it takes for electromagnetic signals to cross the solar system. By June 1976, Viking 1 was approaching Mars, and the final, most critical phase of the mission was about to begin. As Viking 1 drew near to Mars in the early summer of 1976, the team at NASA's Jet Propulsion Laboratory in Pasadena, California, prepared for the delicate orbital insertion maneuver. The spacecraft, having traveled 440 million miles over the course of 11 months, would now need to slow down enough to be captured by Mars's gravity and enter orbit around the planet. This required precise timing and flawless execution of the onboard propulsion system. On June 19, 1976, Viking 1's engine fired and the spacecraft slipped into orbit around Mars. Relief and celebration filled the control room. The first major milestone had been achieved, but entering orbit was only the beginning. The real challenge still lay ahead, finding a safe place to land and then actually landing there. The original plan had been to land on July 4th, 1976, a date chosen to coincide with the 200th anniversary of American independence. It would have been a symbolic triumph, a gift from the space program to the nation during its bicentennial celebration. But as Viking 1's cameras began photographing the proposed landing site in the Chrysae Planitia region, engineers and scientists studied the images with growing concern. The terrain was rougher than they had anticipated. Large rocks and boulders were scattered across the surface, any one of which could damage or destroy the lander during touchdown. Steep slopes and dangerous ridges lurked in areas that had appeared smooth in previous observations from Earth. The dream of a bicentennial landing faded as the team confronted the reality that landing on Mars was far more challenging than anyone had hoped. For weeks, Viking 1 orbited the planet while scientists pored over photographs, searching for a site that offered the best combination of scientific interest and landing safety. Each orbit brought new images, new perspectives, new information to consider. The lander had been designed to handle some rough terrain, but there were limits. Landing on a large boulder or tipping over on a steep slope would end the mission before it truly began. The waiting was difficult, but necessary. Lives were not at stake, as they would have been in a crewed mission, but years of work and hundreds of millions of dollars hung in the balance. More importantly, the scientific objectives of the mission required that the lander survive and function. One chance. They would get one chance to land safely, and if they chose poorly, everything would be lost. Meanwhile, Viking 2 had arrived at Mars on August 7th, entering its own orbit around the planet. Now, 2 spacecraft circled the red planet, their cameras mapping the surface in ever greater detail, searching for the perfect combination of scientific opportunity and operational safety. Finally, a decision was made. A site in the western Chrysae Planitia, a vast low-lying plain in Mars's northern hemisphere, appeared to offer the best chance of success. The region was relatively flat and smooth, with fewer large rocks than other areas. Ancient channels suggested that water might once have flowed through this area, making it scientifically interesting. Most importantly, computer simulations indicated that the lander should be able to touch down safely. The date was set, July 20th, 1976. By a remarkable coincidence, this was the 7th anniversary of the Apollo 11 moon landing. 7 years earlier to the day, Neil Armstrong had taken his famous small step onto the lunar surface. Now, an unpiloted spacecraft would attempt to take humanity's next great step, landing successfully on Mars. As July 20th approached, the tension at the Jet Propulsion Laboratory grew. Everyone involved in the mission knew that the next few hours would determine the success or failure of years of effort. The sequence of events required for a successful landing was complex and had to execute perfectly, with each step depending on the success of the previous one. And it would all happen automatically, governed by pre-programmed instructions, because the vast distance to Mars meant that radio signals took more than 18 minutes to reach Earth. By the time controllers on Earth knew what was happening, it would already have succeeded or failed. The stage was set for humanity's most daring attempt yet to touch another world. In the early morning hours of July 20th, 1976, by Earth time, the Viking 1 lander prepared to separate from its orbiter companion. The spacecraft had been functioning perfectly, all systems nominal, all instruments ready. The moment that thousands of people had worked toward for years was finally at hand. At 8:51 UTC, small explosive bolts fired, and the lander gently separated from the orbiter. For a few moments, the two spacecraft drifted apart, the orbiter's cameras capturing images of its departing partner against the rust-colored backdrop of Mars below. Then, the lander fired its deorbit engine, beginning its descent toward the planet's surface. There is something profound about this moment of separation, something that speaks to the nature of exploration itself. The lander was now committed to its course. There could be no turning back, no rescue if something went wrong, no human intervention to correct an error. It would succeed or fail on its own, guided only by the instructions programmed into its computer and the careful design of its systems. As the lander fell toward Mars, traveling at more than 3 miles per second, mission controllers on Earth could only wait. The radio signals that would tell them what was happening were still racing across space at the speed of light, carrying information about events that had already occurred. This delay, this enforced patience, is one of the unique challenges of interplanetary exploration. Unlike the Apollo missions, where controllers could communicate with astronauts in real time, Viking's fate was already decided by the time anyone on Earth knew what was happening. The lander plunged downward through the thin Martian atmosphere. At an altitude of about 250 kilometers above the surface, moving at a velocity that would have seemed impossibly fast to any human observer, the spacecraft began to feel the first whispers of atmospheric drag. The Martian atmosphere, though less than 1% as dense as Earth's, was enough to begin slowing the craft. Heat began to build on the aeroshell, the protective covering that shielded the lander during its fiery descent. Temperatures rose to hundreds of degrees as friction with the atmosphere converted kinetic energy into heat. This was a critical moment. The heat shield had to protect the delicate instruments inside, while simultaneously slowing the spacecraft from orbital velocity to a speed at which parachutes could be deployed. During this phase, even as it was being buffeted by the forces of entry, the lander conducted science. Instruments measured the composition of the Martian atmosphere, gathering data on temperature, pressure, and chemical makeup at different altitudes. Every measurement was valuable, adding to humanity's understanding of this alien world. At about 6 kilometers above the surface, when the lander's velocity had decreased to roughly 250 meters per second, a 16-meter-wide parachute deployed with a sudden jolt. 7 seconds later, the aeroshell that had protected the lander during entry was jettisoned, falling away to crash somewhere on the Martian surface far below. 8 seconds after that, the lander's 3 legs extended, unfolding like the limbs of a mechanical insect preparing to land. Now, the surface of Mars was clearly visible to the lander's instruments. Radar altimeters measured the distance to the ground with precision, while other sensors monitored the lander's velocity and orientation. The parachute had done its job, slowing the craft dramatically, but it alone was not enough to guarantee a soft landing. The final descent would require powered flight. At an altitude of about 1.5 kilometers, the lander separated from its parachute and back shell. For a moment, it was in free fall, dropping toward the surface. Then, with a burst of fire, 3 descent engines ignited. These engines, throttleable and computer-controlled, would guide the lander through its final approach, adjusting thrust to ensure a gentle touchdown. The terrain below rushed closer. Rocks and boulders, invisible from orbit, were scattered across the landing zone. Hills and slopes, craters and ridges passed beneath the descending craft. The lander's computer processed information from its sensors, calculating and recalculating the optimal engine thrust, making tiny adjustments to keep the craft stable and oriented correctly. 50 meters above the surface, 25 meters, 10 meters. The engines throttled back as the lander's velocity decreased. Dust kicked up by the rocket exhaust began to swirl across the ground, a Martian sandstorm in miniature created by humanity's arrival. And then, at 11:53:06 UTC on July 20th, 1976, Viking 1 touched the surface of Mars. The engines shut down. The craft settled onto its 3 legs, tilting slightly on the uneven ground, but stable, safe, intact. Humanity had successfully landed on Mars. For a few moments after landing, Viking 1 sat silent on the Martian surface, performing automatic post-landing checks, verifying that its systems had survived the descent intact. Inside the spacecraft, instruments that had been powered down for landing began to come back online. Computers ran through diagnostic routines. Antennas oriented themselves to establish communication with the orbiter passing overhead. Then, just minutes after touchdown, Viking 1 sent its first signal from the surface of Mars. That signal, traveling at the speed of light across more than 200 million miles of space, reached Earth about 18 minutes later. In the control room at the Jet Propulsion Laboratory, the moment that signal arrived was one of pure, unrestrained joy. Years of planning, months of travel, and nail-biting minutes of descent had culminated in success. Viking 1 was on Mars, and it was working. But the most exciting moment was yet to come. Shortly after confirming that it had landed safely, Viking 1 began to take photographs. The lander's camera was unlike anything that had been sent to another planet before. Rather than using conventional film, it used a scanning system that built up images line by line, like an old facsimile machine. This meant that images arrived gradually, revealing the Martian landscape one strip at a time. The first image that Viking 1 sent back was, appropriately enough, a picture of one of its own footpads resting on the Martian surface. This image, simple though it was, carried profound significance. Here was proof, visible and undeniable, that a human-made object was resting safely on the surface of another planet, functioning as designed, ready to conduct its mission. The image showed the lander's footpad, a circular metal disc sitting firmly on reddish-brown soil. Small rocks were scattered nearby. The horizon was visible in the distance, a gentle slope rising toward an empty sky. There was a slight haze on the left side of the image, likely dust kicked up by the landing engines that had not yet settled. As this first image was being transmitted, a second camera began scanning a wider view of the landing site. This panoramic image would take longer to arrive, each scan line adding to the growing picture of Viking 1's new home. At the Jet Propulsion Laboratory, scientists and engineers crowded around monitors, watching as the landscape of Mars gradually revealed itself. What they saw was at once familiar and alien. The terrain around the landing site was relatively flat, as the pre-landing surveys had suggested, but it was far from featureless. Rocks of various sizes were scattered across the surface, some angular and sharp-edged, others more rounded by eons of wind erosion. The soil had a distinctly reddish hue, the color of rust, the color that had given Mars its nickname. In the distance, gently rolling hills broke the horizon. The Martian sky, visible in the upper portions of the panoramic images, was not the deep blue of Earth's sky or the black of the moon's airless environment. Instead, it appeared a dusty pink, a consequence of fine particles suspended in the thin atmosphere, particles of the same iron-rich dust that covered the surface. These first images from Viking 1 marked a turning point in humanity's understanding of Mars. For all the previous observations from Earth-based telescopes and flyby missions, nothing compared to actually being there, to seeing the surface up close, to experiencing Mars from ground level. The images revealed a world that was neither the Earth-like paradise that early observers had imagined, nor the completely lifeless desert that some had feared. It was Mars, unique in itself, a world with its own character and its own story to tell. Over the following hours and days, Viking 1 continued to photograph its surroundings, building up a comprehensive view of the landing site. Each image was analyzed for what it could reveal about Martian geology, atmospheric conditions, and the possibility of past water. Scientists pored over every detail, every rock, every soil pattern, searching for clues about the planet's history and nature. But photography was only part of Viking 1's mission. The lander had come to Mars to do science, and now, safely on the surface, it could begin its work in earnest. 1 week after landing, on July 28, 1976, Viking 1 extended its robotic arm for the first time. This arm, about 3 meters long when fully extended, was equipped with a scoop at its end designed to collect samples of Martian soil. The arm's movements were controlled from Earth, though with the inevitable delay imposed by the distance between planets. Commands sent from the Jet Propulsion Laboratory would take more than 18 minutes to reach Mars, and confirmation of the arm's actions would take another 18 minutes to travel back. The robotic arm moved with careful deliberation, extending outward from the lander's body, its scoop reaching toward a patch of undisturbed soil a few feet from the lander. The cameras watched its progress, sending back images that allowed controllers on Earth to verify that everything was proceeding as planned. Then, gently, the scoop pressed into the Martian soil and collected the first sample. This was a moment of quiet but profound significance. For the first time in history, material from the surface of Mars was being deliberately collected for analysis by sophisticated scientific instruments. What secrets might this ancient soil reveal? What could it tell us about the history of Mars, about the processes that had shaped this world over billions of years? Most tantalizingly, might it contain any hint, any suggestion of life? The robotic arm retracted, carrying its precious sample back to the lander. There, it deposited the soil into a series of instruments designed to analyze its composition and properties. These instruments represented the cutting edge of 1970s analytical chemistry, miniaturized and adapted for operation in the harsh Martian environment. One instrument, the X-ray fluorescence spectrometer, bombarded the soil with X-rays and measured the spectrum of fluorescent radiation that resulted. This technique could determine which chemical elements were present in the sample and in what proportions. The results showed that Martian soil was rich in iron, silicon, and sulfur, hence the rusty red color that dominated the landscape. The composition suggested that Mars was, in many ways, similar to Earth in its basic chemistry, but with important differences in the relative abundance of various elements. Another instrument, a gas chromatograph mass spectrometer, was designed to detect organic compounds, carbon-based molecules that on Earth are associated with life. This was, in many ways, the most crucial measurement Viking would make. The instrument heated the soil sample and analyzed the gases that were released. Scientists waited eagerly for the results. To their surprise and disappointment, the gas chromatograph mass spectrometer detected no organic compounds at all in the Martian soil, not even the simple organic molecules that meteorites routinely deliver to Mars from space. The surface appeared to be remarkably barren of organic chemistry. This was unexpected and puzzling. Why would Mars lack even the trace organic compounds that should be present from meteoritic infall? Later research would suggest a possible answer. The Martian surface is bathed in intense ultraviolet radiation from the sun, unfiltered by any substantial ozone layer. This UV radiation, combined with reactive chemicals in the soil, might break down organic compounds almost as soon as they form. The Viking landers might have been looking for organic material in precisely the place where it would be most quickly destroyed. But the most anticipated experiments were the biology investigations. Viking 1 carried 3 separate instruments designed to search for signs of microbial life in the Martian soil. Each used a different approach, looking for different types of biological activity. The labeled release experiment added a nutrient solution containing radioactive carbon to a soil sample. If microorganisms were present and metabolizing the nutrients, they should release radioactive carbon dioxide that could be detected. When the experiment was performed, it showed positive results. Radioactive gas was indeed released from the soil sample. The team was initially excited but cautious. They ran a control experiment, heating a second soil sample to sterilize any possible organisms before adding the nutrients. If the results were due to biology, the heated sample should show no activity. To the scientists' confusion, the heated sample also released gas, though less than the unheated sample. The gas exchange experiment looked for changes in the composition of gases above a soil sample when nutrients were added. It too showed unusual activity, with oxygen being released from the soil. The pyrolytic release experiment tested whether anything in the soil could incorporate carbon from the Martian atmosphere, as photosynthetic organisms do on Earth. It also showed positive, though ambiguous, results. These biology experiments generated debate that continues to this day. Most scientists concluded that the results were likely due to unusual chemistry in the Martian soil rather than biological activity. The combination of positive results from the biology experiments, but negative results from the organic chemistry experiment seem to argue against life. If microorganisms were present, they should leave behind detectable organic molecules. The most likely explanation appeared to be that the Martian soil contained reactive chemical compounds that mimicked some aspects of biological activity without actually being alive. But a minority of scientists maintained that the results could indicate the presence of microbial life with chemistry different from Earth's. The question remained open, a tantalizing mystery that would inspire future missions to Mars. Regardless of the interpretation of the biology experiments, Viking 1 had accomplished something remarkable. It had successfully analyzed the soil of another planet in situ, performing complex chemistry experiments millions of miles from Earth. Every measurement added to humanity's understanding of Mars. Every data point helped paint a more complete picture of this alien world. While Viking 1's instruments probed the soil beneath its feet, other sensors monitored the Martian atmosphere. A weather station on the lander continuously measured temperature, pressure, and wind speed, building up a detailed picture of Martian meteorology. These measurements revealed a world with weather patterns unlike anything on Earth, yet governed by the same physical laws that control our own atmosphere. The atmospheric pressure at the Viking 1 landing site averaged about 7.5 millibars, less than 1% of Earth's sea level pressure. This incredibly thin atmosphere was composed mainly of carbon dioxide, with traces of nitrogen, argon, oxygen, and water vapor. By Earth standards, it was barely an atmosphere at all, more like a hard vacuum, yet it was enough to support weather phenomena including clouds, frosts, and massive dust storms. Temperatures at the landing site varied dramatically over the course of a Martian day, or sol. At midday during the Martian summer, temperatures might reach as high as minus 14 degrees Celsius, just barely above the freezing point of water. But at night, with no thick atmosphere to trap heat, temperatures plummeted to minus 77 degrees Celsius, or even lower. This daily temperature swing of more than 60 degrees Celsius was far more extreme than anything typically experienced on Earth. Wind measurements revealed another fascinating aspect of the Martian environment. Despite the thin atmosphere winds on Mars could reach surprisingly high velocities. The lighter atmospheric density meant that even strong winds carried less force than equivalent winds on Earth, but they could still lift and transport fine dust particles. These winds were responsible for the dynamic dust storms that periodically swept across the planet's surface, sometimes growing to engulf the entire planet in a shroud of suspended dust. As the Martian seasons progressed, Viking 1's weather station documented changes in atmospheric pressure caused by the condensation and sublimation of carbon dioxide at the polar caps. During the Martian winter, carbon dioxide from the atmosphere condenses out as dry ice at the poles, causing a measurable drop in global atmospheric pressure. In summer, this carbon dioxide sublimes back into the atmosphere, and pressure rises again. This seasonal breathing of the Martian atmosphere was a phenomenon that had been predicted by theory, but never before measured directly. The lander's cameras occasionally captured images of clouds drifting across the Martian sky. Thin wisps of water, ice crystals formed in the cold upper atmosphere. Early morning images sometimes revealed a delicate layer of frost that had condensed on rocks overnight, only to sublime away again as the sun rose and temperatures increased. These phenomena demonstrated that despite its thin, cold atmosphere, Mars had an active water cycle, albeit one very different from Earth's. Perhaps most fascinating were the observations of dust devils, small whirlwinds that occasionally swept across the landscape. While Viking 1's cameras never captured a dust devil in action, later missions would document these common Martian phenomena. They were testament to the dynamic nature of the Martian atmosphere, showing that this seemingly dead world was actually quite active when viewed on the right scales. The atmospheric measurements from Viking 1 revolutionized scientists' understanding of Martian climate and weather. For the first time, researchers had continuous, long-term data from the surface, allowing them to build sophisticated models of atmospheric circulation and weather patterns. These models would prove invaluable for planning future missions, helping engineers design spacecraft that could survive and operate in the Martian environment. While Viking 1's lander explored the surface, the Viking 1 orbiter continued its own crucial work high above. From its vantage point, hundreds of miles above the Martian surface, the orbiter had a global perspective that complemented the lander's ground-level view. Together, the orbiter and lander formed a comprehensive Mars exploration system, each component contributing unique and valuable data. The orbiter's cameras systematically photographed the Martian surface, creating detailed maps that revealed the planet's extraordinary geological diversity. Ancient highlands scarred by billions of years of impacts contrasted with relatively smooth lowland plains. Enormous volcanoes, including the mighty Olympus Mons, rose from the surface, their flanks marked by lava flows frozen in place. The Great Canyon system of Valles Marineris stretched across a vast expanse of the planet, a geological feature so large it could swallow Earth's Grand Canyon many times over. Perhaps most intriguing were the channels and valleys that suggested water had once flowed across the Martian surface. Some of these features looked remarkably like dried riverbeds, with tributaries branching and merging just as water-carved features do on Earth. Others appeared to have been formed by catastrophic flooding on an almost unimaginable scale. The implications were profound. If liquid water had once existed on Mars in quantities sufficient to carve these features, the planet must have been very different in the past, with a thicker atmosphere and a warmer climate. The orbiter also carried instruments to study the Martian atmosphere from above. An infrared spectrometer measured the temperature and composition of the atmosphere at different altitudes and locations, helping scientists understand atmospheric circulation patterns. An infrared radiometer mapped thermal emissions from the surface, revealing information about the composition and physical properties of Martian rocks and soil. One of the most valuable contributions of the Viking orbiters was simply to observe how Mars changed over time. As the spacecraft circled the planet day after day, month after month, they documented seasonal changes in the polar caps, the development and evolution of dust storms, and variations in atmospheric conditions. This long-term perspective revealed Mars to be a dynamic world, not the static, unchanging desert it might appear at first glance. The Viking 1 orbiter also served as a crucial communication relay between the lander and Earth. While the lander could transmit directly to Earth using its high-gain antenna, the data rate was limited by the lander's relatively small antenna and low power. By relaying data through the orbiter, which had a much larger antenna and more powerful transmitter, the system could return far more data than the lander could have transmitted on its own. This relay function was essential to the mission's scientific success. For 4 years, the Viking 1 orbiter continued to circle Mars, long outlasting its nominal mission lifetime. It photographed almost the entire Martian surface at resolutions far superior to anything achieved by previous missions. It watched dust storms develop and dissipate. It observed the seasonal cycles of the polar caps with unprecedented detail. Each orbit added to humanity's growing understanding of the red planet. While Viking 1 was conducting its groundbreaking research, its twin was preparing for its own landing. Viking 2, which had entered orbit around Mars on August 7, 1976, carried an identical lander ready to explore a different part of the planet. The success of Viking 1 had proven that landing on Mars was possible, but it had also highlighted the challenges and risks involved. Each landing was a unique event, dependent on local conditions at the landing site. The team selected a site called Utopia Planitia, a vast plain in Mars's northern hemisphere, for Viking 2's landing. This location was more than 4,000 miles from Viking 1's site in Chrysae Planitia, offering an opportunity to explore a completely different Martian environment. Initial surveys from orbit suggested that Utopia Planitia was even smoother and safer than the Chrysae region, though the experience of Viking 1 had taught everyone to be cautious about appearances from orbit. On September 3, 1976, Viking 2's lander separated from its orbiter and began its descent. The landing sequence was identical to Viking 1's: entry through the atmosphere, parachute deployment, final powered descent on rocket engines. For those watching from Earth, it was like reliving the tension of July 20th, knowing that, despite the success of the first landing, each attempt carried its own risks. At 22:37 UTC, Viking 2 touched down safely on the Martian surface. Once again, relief and joy swept through the control room at the Jet Propulsion Laboratory. Now, there were 2 successful landers on Mars, 2 scientific outposts separated by thousands of miles, ready compare their observations and reveal more about the diversity of the Martian environment. Viking 2's first images showed a landscape subtly different from Viking 1's site. The terrain was indeed smoother, with fewer large rocks, though still scattered with smaller stones. The soil appeared slightly darker and the horizon more uniformly flat. These differences, though subtle, were scientifically valuable, showing that Mars, like Earth, had regional variations in its geology and appearance. Viking 2 quickly began its own program of scientific measurements. Its weather station recorded temperatures similar to Viking 1's, but with slightly different wind patterns. Its soil analysis experiments yielded results consistent with Viking 1's findings, suggesting that Martian soil composition was relatively uniform across large distances, though with local variations. The biology experiments on Viking 2 produced results similar to those from Viking 1, intriguing, ambiguous, suggesting unusual soil chemistry, but not providing definitive evidence of life. Having two landers operating simultaneously on Mars provided scientists with invaluable comparative data. When a dust storm developed and atmospheric pressure dropped at one site, researchers could check whether similar changes occurred at the other site. When seasonal variations were detected, they could be studied at two different latitudes. The dual-lander approach effectively doubled the scientific return and increased confidence in the results. The Viking 2 orbiter, like its companion, continued photographing Mars from above, filling in gaps in the global map and monitoring atmospheric conditions. Together, the four Viking spacecraft, 2 orbiters and 2 landers, formed the most comprehensive Mars exploration system ever deployed. Both landers continued operating far beyond their designed lifetimes. Viking 1's lander functioned until November 1982, more than 6 years after landing, when a faulty command accidentally disabled its antenna and ended communications. Viking 2's lander operated until April 1980, when its batteries failed. The orbiters lasted even longer, with Viking 1's orbiter functioning until August 1980 and Viking 2's until July 1978, when it ran out of attitude control propellant. The longevity of the Viking spacecraft was a testament to their robust design and the dedication of the teams that operated them. Long after the nominal mission had ended, engineers found creative ways to keep the aging spacecraft functioning, squeezing every last bit of science from instruments that had already far exceeded their expected operational lives. When the last Viking spacecraft finally fell silent, humanity's first sustained presence on the surface of Mars came to an end. But the legacy of the Viking missions would endure for decades, influencing every subsequent Mars mission and fundamentally altering our understanding of the Red Planet. The Viking landers returned more than 4,500 images from the surface of Mars. The orbiters captured more than 52,000 images from space. Together, these photographs created the first comprehensive visual record of another planet's surface, a library of Martian landscapes that scientists would study for years, extracting new insights with each examination. The scientific data gathered by Viking filled libraries worth of reports and papers. Measurements of atmospheric composition, soil chemistry, temperature variations, wind patterns, and countless other parameters provided the empirical foundation for modern Mars science. Before Viking, theories about Mars were necessarily speculative, constrained by the limited data available from Earth-based observations and brief flyby missions. After Viking, theories had to match the detailed, comprehensive data from the surface and orbit. Perhaps most importantly, Viking demonstrated that landing on Mars and operating there for extended periods was technologically feasible. The mission proved that spacecraft could survive the journey, the entry, and the harsh surface conditions. It showed that solar panels could provide adequate power, that instruments could function reliably in the cold and thin atmosphere, and that data could be successfully transmitted across hundreds of millions of miles of space. These were not trivial achievements. Every future Mars mission would build on the lessons learned from Viking. The entry, descent, and landing profile pioneered by Viking would be refined and adapted by subsequent missions. The challenges of operating in the Martian environment, once unknown, were now understood and could be planned for. Future mission designers could draw on Viking's experience, avoiding pitfalls that Viking had encountered and leveraging techniques that Viking had proven effective. The Viking biology experiments, despite their ambiguous results, taught researchers valuable lessons about searching for life on Mars. The apparent absence of organic compounds in surface soil suggested that future life detection experiments should look deeper, perhaps meters below the surface, where material would be protected from UV radiation and oxidizing chemicals. The emphasis shifted from looking for extant life to searching for evidence of past life, preserved in ancient rocks or in protected environments like deep subsurface ice. Viking's geological and climatological discoveries raised as many questions as they answered, and that too was part of its legacy. The evidence for liquid water in Mars's past demanded explanation. What had happened to that water? Where did it go? What caused the climate to change from warm and wet to cold and dry? These questions would drive decades of subsequent research and motivate future missions designed to probe deeper into Martian history. The images of the Martian landscape captured by Viking also had a profound cultural impact. For the first time, people could see what it would be like to stand on another planet. The photographs made Mars real in a way that no amount of scientific data could achieve on its own. They inspired a generation of scientists, engineers, and ordinary citizens to dream of further exploration, of one day sending humans to walk where Vikings' cameras had gazed. In classrooms around the world, children studied Vikings' images, learning about Mars and about the possibilities of space exploration. In laboratories, scientists pored over Vikings' data, planning the next steps in Mars exploration. In engineering firms, designers sketched spacecraft inspired by Viking success, imagining rovers that could drive across the surface, orbiters with more advanced instruments, even eventual human missions. The 20-year gap between Viking and the next successful Mars lander, Mars Pathfinder in 1997, demonstrated how challenging Mars exploration remained. During those years, multiple missions failed, victims of technical problems, budgetary constraints, or simply the inherent difficulty of interplanetary spaceflight. But when Pathfinder succeeded, it built directly on Viking's legacy, using an updated version of Viking's entry and landing techniques. Subsequent missions, Mars Global Surveyor, Mars Odyssey, the Mars Exploration Rover's Spirit and Opportunity, Mars Reconnaissance Orbiter, Phoenix, Curiosity, Insight, Perseverance, each added to the story that Viking began. Each brought new instruments, new capabilities, new questions, and new answers. But all of them owed a debt to Viking, the mission that first showed it could be done. Behind every great achievement in space exploration lies a human story, a tale of dedication, perseverance, and sometimes sacrifice by thousands of individuals working toward a common goal. The Viking mission was no exception. It was a triumph not just of technology, but of human cooperation, creativity, and determination. The engineers who designed Viking systems faced unprecedented challenges. They were creating spacecraft that would have to function autonomously for months, then perform a series of precise, critical operations millions of miles from Earth, with no possibility of human intervention. Every system needed backups. Every procedure had to be tested exhaustively. The margin for error was essentially zero. Many of these engineers worked long hours for years, solving problems that had never been encountered before. How do you design a heat shield that can protect delicate instruments during entry into another planet's atmosphere? How do you ensure that a parachute will deploy reliably in an atmosphere less than 1% as dense as Earth's? How do you build cameras that can function in temperatures far below freezing and in an atmosphere that would corrode or freeze many materials? Each of these challenges required innovative solutions. The heat shield needed to be tested in special facilities that could simulate the conditions of Martian entry. The parachute had to be deployed and tested in vacuum chambers. The cameras had to be designed with heaters to keep them warm and protective covers to shield them from dust. Every component of the spacecraft represented hours of calculation, testing, and refinement. The scientists who designed Viking's experiments faced equally daunting challenges. They had to miniaturize sophisticated laboratory equipment to fit on a spacecraft, adapt it to operate in the Martian environment, and ensure it could function autonomously. The biology experiments in particular required remarkable ingenuity. How do you test for life in a completely alien environment when you don't know what form that life might take or what biochemistry it might use? Many young scientists and engineers got their start on the Viking program, beginning careers that would span decades and include many subsequent Mars missions. They learned lessons about spacecraft design, mission operations, and planetary science that would inform all their future work. In this way, Viking's human legacy extended far beyond the mission itself, shaping the next generation of space exploration. The mission controllers who operated Viking after landing developed deep expertise in working with spacecraft on the surface of another world. They learned to plan sequences of activities around the constraints of the Martian day, to work with the time delays imposed by the distance to Mars, and to troubleshoot problems when instruments didn't behave as expected. They became intimately familiar with the landing sites, giving nicknames to prominent rocks and features until the alien landscape began to feel almost familiar. There were moments of frustration and disappointment. When the biology experiments failed to provide clear evidence of life, many scientists who had devoted years to designing those experiments felt a profound sense of letdown. When technical problems forced delays or limited operations, engineers who had poured their hearts into the mission struggled with the gap between their hopes and reality. But these same individuals persevered, learning from setbacks and finding ways to maximize the science return despite constraints. The families of those who worked on Viking made sacrifices too, Long hours at the laboratory meant time away from home. Critical mission phases required round-the-clock shifts. The stress of knowing that years of work could be lost in a moment if something went wrong during landing or operations took its toll. Yet, these families supported their scientists and engineers, understanding that they were part of something larger than themselves, something that would advance human knowledge and capability. There were also moments of pure joy. The celebrations when Viking 1 landed successfully. The wonder of seeing the first images from the Martian surface. The satisfaction of watching the spacecraft exceed their design lifetimes, continuing to return valuable data year after year. These moments made all the challenges worthwhile. The diversity of the team was one of Viking's strengths. People from different backgrounds, different disciplines, different perspectives worked together toward a common goal. Electrical engineers collaborated with geologists. Computer programmers worked alongside biologists. Mechanical engineers coordinated with atmospheric scientists. This interdisciplinary approach was essential to Viking's success and would become a hallmark of all subsequent planetary missions. Some members of the Viking team are remembered by name in the history books. The project managers, principal investigators, and mission directors whose leadership guided the project. But thousands more contributed in ways large and small, each playing a crucial role in the mission's success. The technician who carefully assembled a circuit board, the programmer who debugged a critical piece of software, the administrator who managed budgets and schedules, the public affairs specialists who shared the mission's discoveries with the world. All were part of the Viking story. The Mars that scientists understood before Viking was in many ways a planet of mystery and speculation. The Mars that emerged from Viking's data was a real world, complex and fascinating, with a history written in its rocks and atmosphere. This transformation in understanding represented one of Viking's greatest achievements. Before Viking, many fundamental questions about Mars remained unanswered. Was the Martian soil similar to Earth's or completely different? Viking's soil analysis provided detailed chemical compositions. How cold was Mars really? Viking's temperature measurements gave precise daily and seasonal records. What was the Martian atmosphere made of? Viking's mass spectrometers determined its composition accurately. Did dust storms affect the entire planet, or just local regions? Viking's cameras and orbiting instruments tracked storms as they developed and spread. Each answer led to new questions, driving further research. The discovery that Martian soil was rich in iron but poor in organic compounds led to theories about oxidizing chemistry in the soil. The measurement of atmospheric composition helped scientists model Mars's past climate and understand how the planet evolved. The observation of seasonal pressure changes caused by polar cap dynamics revealed the intimate connection between the Martian atmosphere and surface. Viking's images revealed Mars's geological history in unprecedented detail. Scientists could see that the planet had experienced different geological eras, with ancient, heavily cratered terrain giving way to younger volcanic plains. The scale of Martian volcanoes suggested that the planet had been geologically active for much of its history, though it appeared to be relatively dormant today. The canyon systems and outflow channels spoke of a past that included liquid water on the surface, implying a very different climate than the cold, dry conditions that prevail now. This geological reading of Mars's history led to a new appreciation for planetary evolution. Mars was not simply a smaller, colder version of Earth. It was a world that had followed its own unique evolutionary path, shaped by its size, distance from the Sun, and initial composition. Understanding Mars's history could help scientists understand Earth's history and the factors that make planets habitable or inhospitable. The question of life on Mars took on new dimensions after Viking. While the biology experiments did not detect life, they did not rule it out either. Scientists began to develop more sophisticated theories about where Martian life, if it existed, might be found. Perhaps deep underground, protected from UV radiation and temperature extremes. Perhaps preserved as fossils in ancient rocks. Perhaps in ice deposits at the poles or in the subsurface. These ideas would guide the search for life in future missions. Viking's discovery that the Martian surface appeared hostile to organic compounds also had implications for future human exploration. Any human mission to Mars would need to protect astronauts not just from the cold and thin atmosphere, but from the reactive chemicals in the soil. Equipment and habitats would need special materials that could withstand the oxidizing environment. These considerations became part of the planning for eventual human missions. The long-term operation of the Viking landers also provided valuable data about the durability of spacecraft systems in the Martian environment. Engineers learned which components were most susceptible to failure and which proved more reliable than expected. These lessons informed the design of future missions, helping to create spacecraft that could survive and operate even longer. Perhaps most profoundly, Viking changed Mars from an abstract object of study to a place. The images from the surface made Mars tangible, a real location that one could imagine visiting. The daily weather reports from the landers made Martian meteorology concrete. The chemical analyses of soil made Mars's geology accessible to study. This psychological shift from Mars as distant abstraction to Mars as real place may have been Viking's most lasting contribution. As the Viking missions wound down and the last spacecraft fell silent, the question on everyone's mind was, what comes next? Viking had opened a door, but the room beyond was vast, with countless corners yet to be explored. The mission had answered many questions, but in doing so, it had revealed how much remained unknown. The years following Viking saw periods of frustration for Mars exploration. Budget constraints limited new missions. Several attempts to send spacecraft to Mars in the 1990s ended in failure, victims of technical problems or management issues. Each failure was a painful reminder that space exploration remained difficult and risky, even with Viking's lessons to build upon. But Viking's legacy persisted, keeping alive the dream of Mars exploration during these lean years. Scientists continued to analyze Viking data, extracting new insights decades after the mission ended. Engineers used Viking's experience to design improved spacecraft. Educators used Viking's images to inspire students. The mission remained a touchstone, a reminder of what was possible when vision, dedication, and skill combined in service of exploration. When Mars exploration resumed in earnest with the Mars Global Surveyor in 1996 and Mars Pathfinder in 1997, these missions explicitly built on Viking's foundation. Mars Pathfinder's successful landing validated an updated entry and descent technique based on Viking's approach. The The small rover Sojourner that Pathfinder carried represented a new capability, mobility, that would be expanded dramatically in subsequent missions. The Mars exploration rovers Spirit and Opportunity, which landed in 2004, took Viking's approach of surface exploration and extended it across miles of terrain. Where Viking had studied its immediate surroundings in detail, the rovers could drive to different locations, examining various rock types and geological features. Spirit and Opportunity's discoveries of evidence for past liquid water confirmed what Viking's images had suggested. Mars once had conditions that might have supported life. The Phoenix lander, which successfully touched down in 2008 near Mars's North Polar region, carried instruments specifically designed to search for organic compounds, using more sensitive techniques than Viking had possessed. When Phoenix confirmed the presence of water ice just below the surface at its high-latitude landing site, it validated decades of theoretical work based partly on Viking's observations. The Curiosity rover, which landed in 2012, was larger and more capable than any previous Mars lander, but it employed entry and landing techniques descended from Viking's pioneering approach. Curiosity's discovery of organic molecules in ancient rocks was made possible by instruments far more sensitive than Viking's. But the search for those organics was motivated by Viking's puzzling results decades earlier. Each successive mission has built upon the knowledge gained from Viking, asking more sophisticated questions, using more advanced instruments, venturing to more challenging locations. The Mars sample return mission, planned for the coming years, will attempt to bring Martian rocks back to Earth for analysis in laboratories far more sophisticated than any spacecraft could carry. This mission represents the culmination of a journey that Viking began. Human missions to Mars, long a staple of science fiction, are now being seriously planned. The technologies being developed for human Mars exploration, habitats that can withstand the harsh environment, life support systems that can operate with Martian resources, entry and landing systems that can safely deliver large payloads, all trace their lineage back to Viking's pioneering work. Viking demonstrated that spacecraft could land on Mars and operate there for years. Future missions have extended those operational lifetimes and added new capabilities. But the fundamental breakthrough, the proof that it could be done, belongs to Viking. Every subsequent success stands on that foundation. The scientists and engineers who worked on Viking could not have imagined all the missions that would follow or all the discoveries that would be made. But they understood that they were beginning something important, opening a path that others would follow. They built their spacecraft to the best of their ability, operated them with dedication and skill, and shared their discoveries with the world. In doing so, they changed forever humanity's relationship with Mars. Among all the questions that the Viking missions addressed, none captured public imagination more powerfully than the search for life. From the moment Viking's biology experiments were announced, people around the world waited eagerly to learn, are we alone? The biology experiments were designed with remarkable cleverness, attempting to detect life without making assumptions about what Martian life might be like. The labeled release experiment looked for metabolism. The gas exchange experiment looked for respiration. The pyrolytic release experiment looked for photosynthesis or chemosynthesis. Together, These experiments cast a wide net, searching for life's fundamental processes rather than specific life forms. When the results came in, they were maddeningly ambiguous. Positive results that suggested biological activity were contradicted by the absence of organic compounds that any known form of life would produce. Chemical reactions in the soil could explain the results without invoking biology, but they required assuming Martian soil had unusual reactive properties, unlike anything found on Earth. For many scientists, the most conservative interpretation seemed inescapable. The Viking biology experiments had detected interesting chemistry, but not life. This conclusion was disappointing, but scientifically sound, based on the principle that extraordinary claims require extraordinary evidence. The presence of life on another world would be extraordinary indeed, and the Viking results, while intriguing, did not reach the level of certainty such a claim would require. Yet, a minority of researchers maintained that the life hypothesis should not be entirely dismissed. They pointed out that our understanding of possible biochemistries is limited by our experience with Earth life. Perhaps Martian organisms use different biochemical processes that wouldn't produce the organic compounds we expect. Perhaps the harsh surface conditions have modified or destroyed organic evidence while leaving metabolic processes detectable. Perhaps life exists on Mars, but in such small numbers or in such unusual forms that Vikings' instruments provided only ambiguous hints of its presence. This debate, which began in the 1970s, continues today. Each new Mars mission brings new data that either supports or challenges various interpretations of Vikings' results. When later missions detected organic molecules that Vikings' less sensitive instruments might have missed, some researchers saw vindication of their skepticism about Vikings' negative organic findings. When evidence mounted for liquid water in Mars's past, the possibility that life once existed, even if it doesn't today, gained support. The question of past versus present life became central to Mars' exploration strategy. If Mars never had life, understanding why not would teach us important lessons about what makes planets habitable. If Mars once had life but doesn't now, understanding what happened, how a living world became apparently lifeless, would be equally instructive. And if Mars has life now, even if only microbes deep underground or in protected niches, the implications would be profound. The discovery of extremophile organisms on Earth, bacteria and archaea that thrive in environments once thought completely inhospitable to life, has changed how scientists think about possible Martian life. Life has been found deep in Antarctic ice, in the hot acid of volcanic springs, in rock miles beneath Earth's surface, and in the harsh radiation of nuclear waste sites. These discoveries suggest that if life ever got started on Mars, it might still persist in protected environments despite the hostile surface conditions. Vikings' greatest contribution to the search for life may have been to demonstrate both the possibility and the difficulty of that search. It showed that we could build instruments to probe for life on another world and deploy them successfully. But it also showed that detecting life, or proving its absence, is far more challenging than early optimists had hoped. Simple experiments with ambiguous results would not suffice. The search for life would require multiple missions, sophisticated instruments, and perhaps even the ability to return samples to Earth for detailed analysis in terrestrial laboratories. Future missions have taken these lessons to heart. Rather than attempting direct life detection, most recent missions have focused on understanding Mars's habitability, whether conditions suitable for life exist now or existed in the past. Missions have searched for water, organic molecules, and energy sources that life would require. They've studied environmental conditions and how they change over time. They've looked for locations where life, if it exists, would be most likely to be preserved or detected. The Mars 2020 Perseverance rover, carrying the most sophisticated astrobiology instruments ever sent to another planet, is specifically designed to search for signs of past microbial life in ancient rocks. The rover is also collecting samples for possible return to Earth, where they can be analyzed with the full resources of terrestrial laboratories. If life existed on ancient Mars, those samples might preserve evidence. Meanwhile, scientists continue to study Viking's biology results, applying new analytical techniques and theoretical frameworks. Some researchers have re-examined the data using modern statistical methods and found patterns they believe support biological interpretations. Others have proposed new experiments that future missions could conduct to definitively resolve the ambiguities Viking encountered. The question remains open, perhaps the most profound question in all of science. Does life exist beyond Earth? Viking brought us closer to an answer, but did not provide one. In many ways, that is appropriate. The greatest questions cannot be answered by a single mission or in a single generation. They require sustained effort, continuous questioning, and the willingness to follow evidence wherever it leads. On a summer day in 1976, a spacecraft built by human hands touched down on the surface of Mars. It was a gentle touchdown, almost delicate, after a journey of millions of miles and months of travel through the void. The spacecraft settled onto its 3 legs, tested its systems, and began to look around at an alien landscape bathed in strange light under a pink sky. For the first time, humanity had successfully placed a functioning scientific laboratory on the surface of another planet, not merely crashing into it or flying past, but landing safely and beginning a sustained program of exploration and discovery. It was a moment that marked a fundamental transition in our species' relationship with the cosmos. We were no longer merely observers of other worlds, but active explorers of them. The Viking mission represented the work of thousands of people over many years, the investment of significant resources, and the application of the best science and engineering that 1970s technology could provide. It succeeded beyond its designers' hopes, operating for years instead of months, returning a treasure trove of data and images that transformed our understanding of Mars. But perhaps more importantly, Viking represented something essential about human nature: our curiosity, our desire to explore, our refusal to accept that our place is limited to one small world. Throughout history, humans have ventured beyond familiar horizons, crossed mountains and oceans, and explored the far reaches of our planet. Viking was simply the next step in that eternal journey, carrying the spirit of exploration into a new realm. The images that Vikings sent back, showing rocks and soil and sky, so similar to Earth's deserts, yet subtly, fundamentally different, reminded us that planets are real places, not just points of light or concepts in textbooks. They are worlds with their own character, their own history, their own story to tell. And now, for the first time, we had touched one of those worlds, not just with our instruments, but with our presence, establishing a foothold, however tentative, in a place beyond our home. As you rest now in the comfort of your own world, picture that lonely spacecraft standing on a distant plain, its cameras patiently watching a sunset of blue and purple and rose. Picture the quiet landscape of Mars, unchanged for billions of years, and when he reached out across the void to touch it. Picture the engineers and scientists who made that moment possible, who dared to imagine and then made their imagination real. The Viking mission is over now. The spacecraft have fallen silent. Their long watch ended, their mission complete. They remain on Mars, monuments to human achievement, slowly being buried by the drifting dust of Martian winds. But their legacy continues in every mission that follows, in every new discovery about Mars, in every dream of eventual human voyages to the Red Planet. And so we close this story, this gentle tale of the first successful landing on Mars, with the image of those two spacecraft, Viking 1 and Viking 2, standing sentinel on an ancient world under alien stars. They carried with them a message of hope, a testament to what humanity can achieve when we work together toward a common goal. They showed us that the space between worlds is not an unbridgeable gulf, but a challenge we can overcome with patience, skill, and determination. May that spirit of exploration that animated Viking continue to guide us as we venture forth into the cosmos. May we always retain the wonder that drove us to send those spacecraft across the void. And may we never lose sight of the simple truth that Viking proved, that we can reach across vast distances, touch distant worlds, and expand the sphere of human knowledge and experience beyond the boundaries of our home planet. Sleep well, knowing that somewhere on Mars, under that pink sky, our first successful emissaries to another world still stand, silent now, but enduring, a permanent reminder of the summer day in 1976 when humanity first successfully landed on Mars.